So let's begin our question answer session. From next session, I will start doing questions from optimization and various numerical tools. So this is the last session for the limits, continuity, differentiability. So we'll complete what are the questions we have to discuss so far. So I'll start with question number 8. So this question is based on true or false. So A part basically asks you if a particle has a constant acceleration, then its position function is a cubic polynomial. So it basically asks you that, let's say I have an acceleration and that is a constant function, right? And we know that acceleration can be written as derivative of speed with respect to time. Okay, so what do we see from here? This is only true if my velocity is a function of time, and that's a linear in time, right? It's a linear function, because the moment I take derivative of this velocity function with respect to time, I would have just a constant. Okay, so the first thing which I understood with the problem, that my velocity is actually a function of time, and that is a linear dependence. But it asks me that the position function is expected to be a polynomial, and that's the question. But we also know that the velocity is actually again a derivative of my position x. So this can only be true if my x is a function of a quadratic, right? Some quadratic function. Then only I can have this particular velocity function, because if I take a derivative of a quadratic function, I will end up with a linear function, and I can explain you in this. For example, if I have a function f of x and that is quadratic, x square plus bx plus c. So what happens when you take a derivative? You reduce the power of x with one value, right? And when you do the integration, you increase the power of x. So the moment you take a derivative of f of x, what do you see here? You see some constant times of x plus some constant, right? So basically what you see here, some constant times of x plus some different constant, which I would say some constant prime, for example. So effectively you see here it's being a linear function. Since I know that the given thing to me, that acceleration, which is a derivative of a velocity, so acceleration was given to me some constant. Let's say that constant is some small k, right? And what I can say that my velocity is a function of a linear function in constant. Then only if I take a derivative of this particular velocity, then I can see that I would get this acceleration as a constant. And since you can also see that I can also have some arbitrary constant here, some arbitrary constant, right? And you can check this. When you take a derivative of the velocity, it will give you an acceleration. And similar process we can again do for the position as well. And the idea is that my velocity is actually a derivative of my position. So what do we see here? See that, but since velocity is given to me as linear, so what do I see? That my position actually turns out to be a quadratic. Okay, some quadratic. Maybe I'll say some k prime, for example. Maybe some ct plus some different constant. Because the moment you take a derivative of this, right, we'll end up with this. If you take a derivative with respect to x, sorry, I have written t, I mean to say x, sorry, t, I'm sorry. So just take a derivative with respect to t, you will end up with this particular expression, and iteratively take a derivative with respect to here, we'll get acceleration as a constant. So what do we see here? To be as a quadratic. not cubic. That's not a cubic thing. Okay, so what we see here, that this turns out to be a false expression. So you might expect this kind of a problems here in exam as well. So we see here that acceleration is actually nothing but a double derivative of a position function. So if my acceleration is constant, then you can expect your position function to be a quadratic, because acceleration and the position function, they are related by a double derivative. So the next part of the question tells you that if there is a function and it is differentiable in open interval, then by the mean value theorem there is a number c such that you can have this. So just basically a definition. You can see that this turns out to be a definition of mean value theorem. This basically tells you that if you have let's say you have a curve, right, this, and so what that basically tells you, let's say example, this is some x equal to a and this is some particular x equal to b, and if you try to calculate an average slope to this particular points, because this coordinate is just nothing but a comma f of a will be b comma f of b. So if I try to calculate what is an average slope, which will turn out to be f of b minus f of a will be minus a, but I can always find an instantaneous slope to some point, I don't know, maybe some x equal to c, but there exists at least one value c belongs to this interval a comma b, such that if I try to calculate what is an instantaneous slope at that c, that turns out to be equal to average slope, right? So from here I can see that my f prime of c is basically f of b minus f of a, b minus a, and at the end you can write down as whatever the problem is stated to us, but just by doing a cross multiplication, dash c for b minus f of a, and provided that a is not equal to b. That's important, because then only you can have this multiplication, otherwise you can't. So you can see that's a true statement. It's true, they always exist. That's what a mean value theorem tells you. So this statement turns out to be a true statement. And then let's go to the third point. So they tell me that there exists a function f of x such that this particular limit exists and that is equal to 0. So the question is that this particular limit, is this true for all k? I mean, that is given to me, that is true for all k. So what do we can comment about this particular function for large? I just want to see the behavior of the function fx for a large input, because what we see that the behavior of this particular function turns out to be 0 for a large input. And for me this particular statement is true. It doesn't matter whatever x is, whatever the value of k is, unless and until it's a constant value. And the idea is very simple. The idea what we have here is that turns out to be 0, because this particular class kind of limit actually falls under the class of this, where you have two functions, let's say g of x and h of x, okay, and sorry, infinity here, and this turns out to be 0 if your limit of the denominator goes to infinity. I mean, yeah, because what happens in the numerator, you have some finite value, and in the denominator you have something called as very large value, and that is approximately 0, right? Basically, you're trying to divide a very small quantity into infinite pieces. That's what fraction tells you, right? So that's what it means. That means each individual get almost 0. So that's what the limiting behavior tells you. So this statement is true. That's true. That is true for all number k. So this statement is true. And let's go to the D part. So if f of x has an absolute minimum at x equal to 3, then f dash of c is equal to 0. Is this statement true or false? See, first we need to understand the situation. What is the situation here? So the statement they gave me is that f of x has an absolute minimum. Absolute minimum. They didn't told me that that's a minima. It just told me that that's an absolute minimum. That means the function takes a minimum value at that point, at x equal to c. But my issue is, you might have a situation, for example, let me draw a picture for that. Let's say you have a, for example, this. Let's say you have this x equal to c, for example, and you have this other maxima minima. For example, this is the maxima, this is minima, maxima, minima, and let's say this is just a flat line, right? So over here also you have basically this 4 point also have derivative equal to 0. But here you can see that over here my f dash c, you can see that that is not 0. You have some slope here, and that slope is defined by the right hand side of the function. Let's say my function starts with exactly x equal to 3, okay, and this is the trajectory I have. So what I can see here, that I can still have a non-zero slope here, right? X equal to 3, and also you can see that the function has a minimum value at x equal to 3. That's what the minimum value, absolute minimum value, right? Okay, so if the question was framed in such a way that f of x takes absolute minimum value at x equal to c, such that c belongs to some interval, some closed interval a to b. I mean, you are not considering that c to be some boundary point. If c turns out to be some boundary point, then you can still have a minimum value without giving the condition that you need to have a maximum minimum, right? Over here I can see that maxima is somewhere here, and that's not maxima and neither minima, that's just a flat line. So you can still have the absolute maxima and minima. You can still also have this situation, right, in which you have this particular kind of plot. Listen, you can see all these points are minima, absolute minima, absolute minimum value, not minima, sorry, absolute minimum. But that's true. Over here you have the still derivative to be equal to 0. Over here also you have the derivative 0, here also have a derivative 0, and all these points have derivative 0. That's true. But if that C point turns out to be some boundary point, then this derivative thing might not necessarily be true. So what in general we consider whenever we see such statement, we interpret those statement as if that this point x equal to C is inside the given interval, not at the boundary point. They are not the boundary point. We usually consider them to be this kind of point. This exactly this kind of C. Then you can see, yeah, then you need to have this particular maximum minimum thing to happen. So this statement is true provided x equal to C is not boundary point. Then you might have trouble. Okay, so this is true provided the x equal to C is not a boundary point. Okay, so let's go to the next part, that is the 9th. Basically again we have to say whether this statement is true, false, and have to justify it with a brief answer, like why is it true, why is it false. Okay, so the A part basically tells you that there is a differentiable function f of x with the property that f of 1 is minus 2 and f of 5 is 14 and f dash x is less than 3 for every real number. Okay, so first information they have given is this, that my function is differentiable. That's very important. If it is differentiable, that means that is continuous. That means you can still have a line without lifting a pen. With the property that's the additional property that they have mentioned here, that f of 1 is minus 2 and f of 5 is 14. That means you can see that if I multiply this f of 1 into f of 5, that will turn out to be negative. That means the function must cross x-axis at least once in between 1 and 5, right? So I can tell you geometrically what does it mean. Means that, let's say this was your axis and let's say this was your curve, and over here this was my x equal to 1, right? And x equal to 1, I can see that the function is this, it takes value minus 2 according to the problem over here. But you can see that x equal to 5, the function takes 14. So let's say this is x equal to 5 here, and we have this particular point here, we have 14, and the information told me that this function is differentiable. That means it must pass at least once to the x-axis. It must cut. That means there exists a root in between 1 and 5. At least one. So the idea is that we use the fact that f of 1 times of f of 5 turns out to be negative. That means there exists this particular intersection. And importantly, statement they have asked me to prove is that this derivative is less than 3 for all real x. They have asked me to verify this. F dash of x is less than 3. Is this true? Can you conclude this? Let's check. Let's check. How can we check this? We will do this. We will first find what is the average slope. Okay, well, first we'll check what is the average slope, and we'll see with respect to x equal to 1 and x equal to 5. So the way we can check the average slope, we first check see the negative difference in the y-axis, then difference in the x-axis, and this turns out to be 14 plus 2 is 16, 4, which turns out to be 4, right? And this is what an average slope is. But using my Lagrangian mean value theorem, Lagrangian mean value theorem, it basically tells me that there exists a particular C, x equal to C, where the instantaneous slope will be equal to the average slope. They exist, right? They exist. But to me, they have told me to verify this. So how can we relate them? That's the question. And they have asked me for all real values of x. That's important. Let me write down here as well. For all x belonging to the real number. What do I see here? Because of the Lagrangian mean value theorem, there exists C for which my average slope is 4. I mean, for which exists one instantaneous slope which has a slope 4 not equal, not has a 4 which is definitely not less than 3, right? That means the statement which is given to me, that's false, right? Because the statement tells you that each and every instantaneous slope is less than 3. But because of the analysis which we did here, which tells me that there exists one instantaneous slope which is equal to 4. That is not less than 3. Right? So what we see here, that this particular statement is false. Okay? Because there exists one particular instantaneous slope for which we have slope equal to 4, which is not less than 3. So that is false. I hope the idea is very clear over here. You can see that. The next step is there is a function which double derivative is equal to 0 for a 5 input. Then they have asked me that is this coordinate is the inflection point for the given curve, right? So the idea of the inflection curve, which I have told you, that the first derivative is 0 and second derivative is also 0. That's what the characteristics of an inflection point. Since if you don't remember, I can make you recall that inflection point is basically the point at which the concavity of a curve change. For example, let's say we have this particular curve, and you can see I am calling that this particular point is an inflection point, because at this point at the left you can see that the concavity is different, and that concavity is this, right? You can see this is concave up, and over here it's concave down. Concave down, you can say it's concave up. So this transition of this concavity of the curve, the curvature of the curve, right? I mean to say the curvature of the curve is happens when it passes through this inflection point. Inflection point, I mean to say, not inflection point. Inflation means something else. Okay, so and you can see that over here the first derivative might not be 0. The first, let's say this is inflection point, let's say at x equal to c sum. So first derivative might not be 0, but definitely the second derivative is 0. You can have first derivative equal to 0, for example, in the case of x cube. In the case of x cube, you can see that you have this kind of a curve, where you can see here this x equal to 0 is an inflection point, and you can see here that let me write it completely, that's x cube, and you see that my first derivative at 0 is also 0, second derivative is also 0. So that's a special case where your first derivative is also 0, but in general the first derivative might not be 0, or second derivative is for sure 0, because at the inflection point you can see the behavior of the curve is like a straight line, and straight line has a double derivative 0. That's a simple thing. So that's the idea and the notion of something called as inflection point. And what is given to me that the double derivative at 5 is 0. So just want to know, let's say this is my behavior, and this is some behavior here, okay, and expectating like this coordinate phi comma f of 5 is this inflection point. Is this inflection point? That is the question mark. Nothing they have given me the second derivative is 0. So yeah, it is 0. That's true. That's an inflection point because it satisfies all my definitions of the inflection which I have discussed so far. First derivative might not be 0. It might be 0. That's not a necessary condition. But this is what turns out to be a necessary condition. I guess necessary and sufficient. Sufficient as well. If you just check this much is enough. Necessary means this has to be true. Let me first clear the difference between necessary and sufficient. Sufficient means that if you check this, then this checking is enough to conclude. Okay, but when I say necessary, that means you have to check this. Without checking this, you cannot conclude. When I say necessary and sufficient condition, that means you have to check this, and checking this itself enough. So you have both qualities together, and this is very good. I mean, this is what actually tells you theorem. Because in order to prove a theorem, you need to check necessity and sufficiency both. It's like a double implies kind of a statement, right? Double implies. You have to check otherwise as well. If I'm saying left hand side, left to right is true, then you also have to check whether right to left is also true. If both are true, then you say it's double implies statement. And let's say left to right means necessity, and right to left is sufficiency. So this is how you prove a theorem. So what turns out to be this particular thing turns out to be necessary and sufficient. So just by checking the second derivative, it's enough to say that you have inflation point as far as one dimension is concerned. So that's the idea. So yeah, that's true. This is true that this is the inflection point. Then we have a third statement which tells you that the first derivative is 0 and f of x has a local maxima or a local minima at x equal to c. See, if a first derivative at a given point, they have not talked about the neighboring point. What if the neighboring point also has the derivative 0? What happens? Then is it the local maxima or minimum? What is this? Is this local or maxima minima? You can have this particular idea, right? This. What about this? You still have derivative is equal to 0. Okay. So this is not a local maximum minimum. But I guess in the question they are only interested in that for a given point, not for a given range. That's the difference here. So for a given point, yeah, that can be a local maximum and minimum, but not for a given range. So try to make a difference between them. They are different things. Over here they are for a given range, and here you can see they are for given points, given isolated point, I would say. So what happens basically in the neighborhood, they have the highest value or maybe the lowest value because they follow the idea that the first derivative is 0, because that's the only point where you can have this, horizontal lines, which is the signature of maximum and minimum. So this statement is also true, but you have to be very careful for this kind of a cases. I would say you need to be cautious. So be cautious. The caution of such cases. So keep that in mind. And so basically the D statement asks me if f(x) is a differentiable function and the equation f dash x equal to 0 has two solutions, then the function has no more than three solutions. So what does this basically tell you? That the first thing to tell me, function is differentiable function. That's good because that's continuous. That's the most important thing. And they told me that there exists two roots of a first derivative. That means there exists two critical points, right? So this is basically this particular statement, nothing but it tells you that it has two critical points. Okay. So the question is, and the function has no more than three solutions. How can we interpret this? If we check. So way we can check is just writing all the values of x differentiable. That means I don't have to lift my pen. I can have a continuous line. And they told me that f dash x equal to 0 has two solutions. That means if I try to make a plot, so I have to first mark down my maximum value, right? Let's say my maximum value is 1 at x equal to c1, and let's say x equal to c2. These are my two solutions. These are two critical points, and we know that we cannot have a two local maxima nearby. We cannot have a successive local minimum and successive local maxima. We cannot have, right? So there might be cases such that you have a maxima here, you have a minima here, and you have this kind of points. You might have this kind of a plot. Let's say f of x and x, but you still see that there is only one solution, one root, only one root. So at least I would say I at least found a root, right? At least a root exists. That's surprising thing, right? Because I just concluded from nothing, almost. Just using these two ideas, I came to know that f of x has at least one root. But at max, how many root it can have? That's interesting. Because let me just have a copy paste of this. Because now you can have a situation like this, in which okay, here you have this maxima, here you have this minima, and you have this kind of a plot. Okay, so what you can see here, I have one maxima, sorry, another root 0, another root 0, another root. So in total I have at max three roots. So I can have at least one root and at max three root. I can also have two roots, one distinct root and two of the root will be my identical root. You can say equal root. And the way I can have that particular diagram to show here is by this. Let's say two of the roots coincide. Then what can happen here? Here you have maxima, and let's say the minima is this. Okay, so you can see have this root and this another root, right? I can have in both the cases I have two maxima, two critical points, again two critical points, where I can see my maximum minima, right? Over here also I can see. So at max I can have three roots, at least I can have a root, or you can also have a situation in which you have one distinct root sorry, I mean to say two distinct roots. Let me write it this way, this would be good. One distinct root and two coincident root. Okay. So this is what my analysis is from the given information to me. So the statement tells me that then the equation f of x has no more than 3 roots. That's true, right? Because that's what we proved here. At max function can have 3 roots. So this is what the exact statement this B part asks. So that's why I like this question, because this question teaches you how to do the analysis, and that's what I guess it is expected in the question paper as well. So you can expect this kind of a question in your paper, and we found that this is true. Sorry, this is true. Okay. Then the next part of the question is, if function is increasing at a given interval 0 to 1, and that's a closed interval, then the square of the function is increasing on 0 to 1. Is this true? I don't know. Let's check it. Let's check out. The way we can check out is, let's say this was given to me, right? F dash of x is greater than 0 for all x belonging to 0 to 1. So that's what the increasing function is. Right? Honestly speaking, it should be greater than equal to, because even if it remains, if the f of dash remains equal to 0 for a given isolated point, it's fine. Like you can still have this kind of a growth here, right? But you can have a momentarily flat horizontal, almost constant, then it increases. So this is just increasing. But you have this particular kind of inequality, which basically tells you it's a monotonic. That has to be strictly greater than 0. So just to include the case of where you can have a momentarily 0 slope, I'm including this greater than equal to sign. So that's the reason behind why I'm including this equal to sign, because just to include that particular cases. Because in the problem they have not told me that that's a monotonically increasing. Okay. So the idea is, now what if you now the new function which I have defined, which is basically taking a square of original function. The way we can check whether it is increasing or decreasing, you have to take a derivative with respect to x, and that turns out to be, you have to just use the chain rule, because you have over here that's a composition of two functions. I'm writing this detail for those students who don't know how to do the differentiation of a composition function. Basically composition of two functions where you have this x square and f of x. Okay, so here you can see you have this substituted f of x as an input of the x square function, and hence you end up with this f of x function. The moment you take a derivative of this function, this will turn out to be this. Okay, and interestingly, I know that my f dash of x is greater than 0 for all x belonging to 0 to 1. But what about the f of x? Is this positive for all x belong to 0 to 1? I mean, that is not given to me, right? My f of x can be negative as well. I don't know, what is this? Is this f of x is positive or negative? That is not given to me. You know, you can have this kind of a situation in which you can have this, right? This kind of a function, let's say f of x to be this for example. This is my 0, and let's say this is my 1, and you can see that from here to here you have a negative value of f of x, but from here to here you have a positive value of f of x. You can see from here, right? From here to here positive value, from here to here negative value. So f of x can can have a both signs, right? But the key idea is it is still increasing, right? That's an increasing function, but still that's an increasing function. So since we don't know what is the sign of f of x, so f of x might be negative. So, h dash of x can be positive, can be 0 for a given point. So the basic idea is it can be, greater than equal to 0, it can be less than 0, depending on the sign of f of x. But for sure the f dash x is positive. So when f of x is positive, when f of x is negative. I hope this idea is clear, right? What is happening here? I hope this idea is clear to us, because f dash of x is greater than equal to 0 for 0 to 1, right? So I have no problem with the f dash x. But since I have this particular thing, right? You can see h dash of x is basically a multiplication of f of x and the derivative of f of x. I know the derivative is always positive in that given range, but I still can't conclude what is the sign, what is the value, sign of the value of f of x, right? So f dash x can be positive, negative, depending on my function. So yeah, so that's an inconclusive. So the way you can write down is, we always take a general situation, and generally it's not increasing, right? That's not an increasing function. So we can conclude that this problem set, this E part, is false. You can still have non-increasing behavior of the square of increasing function. Okay, and how can you conclude that? And the way we can conclude that, let's say I just want to verify this, is this true or not? We can take this the idea of this example, like here, this is the example. See if I'm able to, so that this is in your note. You can check them out. Now let's get back to our problem sheet, and we will see the question number 10, where again we have this true or false statement, and we'll try to justify whether this statement is true or false. The A part basically asks you, if I have a function f(x) which has a vertical asymptote, that is, important function has a vertical asymptote at x equal to 1. If it has a vertical asymptote, so basically asymptote means you have infinitely irremovable discontinuity, right? You have infinite discontinuity at that x equal to 1, and you cannot remove that. So what do we see here? Since you have infinite irremovable discontinuity, we know that there cannot be exist any limit. I mean, this is false. I mean, for sure, s is not a finite value. So this statement turns out to be false statements, because L does not have a limit, just because it has a vertical asymptote. So this turns out to be a false statement. Let's go back to the B statement. So if a domain is a positive for a given function and has no horizontal asymptote, the horizontal asymptotes are different than the vertical asymptotes. For example, I can give you this example as an horizontal asymptote. Let's say you have this function f of x 1 minus e to the power minus x. Okay, and this is true definitely for all x belonging to R plus. And I just want to see how this function is going to behave for large value of x. Okay, and clearly see that at x equal to 0, this function gives me 0. Starts from here, and it makes an asymptotic behavior. So you can see this is acts as an, so this particular line so you can see this y equal to 1, which is a horizontal line, acts as an asymptotic, horizontal asymptote for the given function. So this is what it means to be existence of horizontal asymptote. This kind of picture you can have in your mind. So this is 0 and this is 1, and over here you have this f of x function. This is your x, and here is the plot of the given function which I have shown to you. So you need to be careful like what I have done here. So this is not a thing, that's a abstract representation. So this is your horizontal asymptote. Basically, where the function is trying to make a saturates. Function trying to increase, but as you increase your x value, input value, the function goes and saturates to the given output 1. It is very close to 1, but it never exactly equal to 1. It can never be exactly equal to 1, but it will be as close as possible. The more you will increase the value of x, the more the function will be very close to 1. So that's basically the idea of horizontal asymptote. And in the question you can see that, and they have said there are no horizontal asymptotes. That's important. Okay, because the moment you have an horizontal asymptote, then what happens in the case of horizontal asymptote? You can see the function, the derivative. Let's say if you take a derivative of the function, this will approach to 0 as your x tends to 0. That's what the definition of the horizontal asymptote you can have in your mind. For example, here you can see from here. So this is what an asymptotes behave. This is how an asymptotes behave. You might have in general asymptote. For example, this is also an asymptote, and it gives you wonder that over there exists only vertical and horizontal, but that's not true. For example, if you consider this function, let's say
okay, I found this on the web for Lai says. Check it out.
Let's say this example, this particular function, it has an asymptote as y equal to x as an asymptote, because this function has a plot of this, and the minima occurs at x equal to 1, and the minimum value of this function at x equal to 1 is 2. This is one of the examples where you have neither vertical nor horizontal. It is some in general straight line, right? So the idea is that asymptotes are nothing but the straight lines. Straight line, you can say behavior, limiting behavior. You can say it's a limiting behavior. Straight line limiting behavior of a function. That's what an asymptote is. So you can see that this function behaves like an y equal to x for a large value of x. So that's the idea of the asymptote you can have in your mind. So this function has no asymptote in the given domain, and the question they have asked, does the limit the value of the function at large input is plus or minus infinity? So you understand that from here, since it doesn't have any horizontal asymptote, yeah, then this might be true. This can be true, right? Because I can give you an example of function. Let's say function f of x equal to e to the power x, which doesn't have any it has a vertical horizontal asymptote. For example, the x-axis. In this case, let me give an example. For example, f of x equal to x. This function don't have any asymptote. It's just this. So you can say function takes positive and positive infinity for positive large x, negative infinity for negative large x. So yeah, this definition, this particular thing is true. This might can go to any value, plus or minus. But the idea is that the plus or minus will be together. I mean, it depends on the function we will choose. That's the idea. So that's true over here. But this question actually teaches you the concept. Now the next question is g of x equal to x square, then is this true? We just want to check. The way we can check is, and since we don't know what is the g of 2, in this case I don't know what is g of 2, or do I know? We'll see. G of 2 is 4. The way you can check this by substituting x equal to 2 here, and if you just try to calculate this turns out to be a 0 by 0 form. And the way you can avoid this situation by taking derivative on numerator and denominator both. So what do we see here now? That this whole particular limit is nothing more than just x tends to 2 f dash of x. So basically what you have to do, take a derivative of this and substitute 2. That turns out to be twice of 2, and that's equal to 4. And you can see that this is not equal to 0. That's what we see here. So this statement is false. We just proved it. That it has a value equal to 4. By the way, this is the definition of a differentiation at 2. That's a definition. I mean, definition of derivative at x, sorry, at x equal to 2. So you can expect that that is not equal to 0, because we know the derivative at x equal to 2 is not 0. The derivative actually increases as you increase your x. You can see that from graph as well. So this is false. That's not true. And if you check out the D condition, if the double derivative of 2 is 0, then this is a inflation point. Yes, that's true. We just had the similar question upside, and I mean the above case, for example, where we had this over here, the B path. Same question. Again repetition. Okay, so that's true. So the E part basically tells you that have a first derivative at C, which turns out to be 0, then f of x, the function has a local extrema at C. This is true provided C is not a boundary point. We just had a discussion this, right, over here. You can see from here itself. At this diagram we had the discussion, if C is a boundary point, then you might not have the condition that the first derivative is 0, but still you have this absolute minimum value. So you can see this question is again a repeat that what we have did earlier, like this, again a repeat, but instead of C they have just put some other values. And one more thing, like they have, okay, yeah, I mean same statement, basically they have wrote it in another way. They have used the word extremum instead of using maxima and minima, so they mean same. Okay, maxima or minima, you can see this and this together they are called as extremum. So that's an English word you need to know. So now the F part is, if a function has an absolute minimum at C, then f dash C is equal to 0. Might not true, right? Because the same statement which I have told earlier. This is true if C is not a boundary point. Okay, so again you have to, this statement is true, but you have to always keep in your head that C, if C is not a boundary point, then the statement is true. If C is a boundary point, then the first derivative equal to 0 might not be true. Okay, and yeah, the next question is, the question they have asked, if f dash C exists, then this is true. That's an interesting question, because what I'll do now, I'll use the definition, one of the definition, that f dash C is nothing but my f(x) tends to C f of x minus f of C x minus C. This is one of the definitions, right? And I will try to use this because in the question they have told me this guy exists, and the way I can verify this by solving this, because I know that on the right hand side we have this 0 by 0 form. So by taking L'Hopital rule, you can just justify this particular statement here. But in the question they have asked me about this. Then is this is this numerator equal to 0? That turns out to be true. Yeah, that turns out to be true, right? Because the idea is existence of this derivative means function is continuous, and if the function is continuous, that means if you calculate a limit at that point, that has to be equal to this. That's what the continuity tells you, right? So that's the idea behind it. It just basically tests you the knowledge that if a function is if the derivative exists, definitely the function is continuous. So this question is also done. So the answer is true. The H part. So the H part basically tells you that f of 1 is negative, but f of 3 is positive. If you take a multiplication of them, that turns out to be f of 1 times f of 3 is negative. That means you can just use the same argument which you have discussed earlier. Exactly this same argument from here, exactly same repetition, you can do this same exercise to justify that f of C is equal to 0. There exists, right? Because you can see from here there exists at least one root, at least one, and that's what the question basically asks you. Yeah, there exists, see. Right, this one. So this is true. This basically tells you, mean value theorem, the application of mean value theorem. So yeah. Now let's go to the ith point, where you have a derivative of a function. Derivative of a function. Don't take this g to be some function. See over here, g is some variable. So you see that g is some variable. Okay, just don't see that g to be some. Don't get fooled by seeing this g to be some function, a concatenation of function. It might be some concatenation of function, but for now you just have to see that this g is some variable. Instead of x, now we are writing g. But you can see from here that function exists. The function exists except at g equal to 3. you can see g equal to 3 is not included in this interval. And the reason behind that, because this derivative, because you can see that this derivative because you can see from here that this interval g is not equal to 3, and from here if you check the domain of this function, turns out to be g belongs to R except except g equal to 3. So this solution just basically a test whether do you know how to calculate the domain of a function or not. So the answer is true, because the domain has given right. So this is the way we can see the function is differentiable to what values. So you calculate your derivative and check the domain of that. Since you know, once you find the proper domain, you can see that for this value the function is differentiable, the original function. Similar question like over here, where they have asked to know what is the equation of tangent at this point. Oh, come on. At this point. And the way you can calculate, same way, you have to solve this question generally, so that whenever you see such type of question, you know what to do in this case. So the question, you can see they have given me f dash of x, this is given, okay, and they have given me a point, let's say x naught y naught at point, okay. That means you know what is this, right? You know what is this? You know the slope at that given point, and the only difference is that you know the equation of tangent. We will use this slope point form, which turns out to be y minus y naught x minus x naught. And in case you're wondering how this geometrically looks, you can have this let's say this was my point at which I am finding this slope. Let's say this x naught and my y naught, right? So the coordinate is x naught comma y naught, and you know what is this function. So they are just basically trying to know what is the equation of motion of this. No, not equation of line. So this is the procedure. Okay, this is the procedure. That's the idea. So, and you can just apply this on this given problem, and you can see that to me the point is 0 comma 1 over 3. The given point is 0 comma 1 over 3, and f dash of g is given to me as 3 minus c whole square. Then f dash of 0 turns out to be 1 over 9. So my equation of motion is 5 minus 1 over 3 equal to 1 over 9 g minus 0. So what do I see? I see this g over 9. Yeah, I can see 3 over 9 and y minus 1 over 3. The same exact. So this is true. Okay, so that's the idea. That's how we solve this kind of a problems, which is quite general. I mean, we will encounter them every time. So the 11th question, basically again a true or false question, where the first A point basically tells you the points described by the polar coordinates are the same. So first of all, I need to tell you what are the polar coordinates in case any of you guys don't know. So the polar coordinates are basically r comma theta. So if you have this kind of a coordinate system where we describe everything in terms of, x, in terms of x comma y, then you can have another coordinate system which is just not like this, which is not like this. This is more like this. We have concentric circles, and okay, so this concentric circle represents different values of r. For example, the inner circle basically tells you r equal to 1. Let's say the second line, the second circle basically tells you a distance. Let's say r equal to 2. The third basically tells you the r equal to 3. So basically all the points on this circle have same distance from the origin, right? And the way you can have that kind of idea is only through a circle, right? So we have coordinate, one of the coordinate axis like this r is going outside, away from the circle, right? And there is another coordinate that is in the terms of angle, right? For example, which is going like this way, it's going in a circular way along the circle. Okay, the first coordinate is like which circle, and the second coordinate tells you where on the circle, right? Because this point is basically your theta equal to 0. Let's say, I mean, from here we start measuring our angle. Let's say this theta would be equal to some maybe 45 degrees. Let's say this theta would be equal to 90 degrees, and let's say this theta is just 135 degrees, and this theta is 180 degrees. So likewise, you have this angles, right? It basically tells you where it is on my circle. So let's say I have a general point, let's say this, and I want to write down the coordinate of this, and I want to write down what's the coordinate of this. So I will express in the terms of r and theta. So I can see here over here my r is 2, right? But if you check the angle over here, let's say the angle over here is 30 degree, right? Let's say, for example, so in this case my angle would be minus 30 degree, minus, because we are considering this horizontal line, which is this line, to be our reference of angle, right? Like the way we have origin, which is the reference of distance. Alright, so this particular line, this particular thing is basically my reference. So you can see that this particular coordinate which I have shown earlier turns out to be 2, minus 30 degree. What happens, we often don't write the angles in terms of degrees. We prefer to write them in the terms of radians. I know that in the radians, this minus 30 degree is actually nothing more than minus 5 over 6. Okay, so that's how we write down our polar coordinate system. And in case you want to know what is the quick formula of converting this from xy. So this is my xy, right? And you can see that you can have the same point here. Let's say this is some point P. It's again point P, which has a coordinate x comma y. And in case if you wonder how to calculate this, so the way we can calculate this, because you can see here, this was my point, and if you check this, this is my angle, right? And so my angle is minus tan inverse pi over x, sorry, minus tan inverse y over x, and r turns out to be under root of x square plus y square. Sorry. I think so. Wait a minute. So this is how you can convert from an xy coordinate to ry, theta r coordinate or r theta coordinate. Okay, so that's the idea. But what happens if you have theta r coordinate? Let's say you have this coordinate, r theta coordinate. So how will you convert this coordinate into this xy? And the way we can do this, let me give an example. I have here explained you how we have did this, right? Because you can see that over here, in case if you still didn't understand, you can see you have this right angle triangle over here. And one of the perpendicular distance is x and another perpendicular distance is y. And this turns out to be the r. So this is how you do this calculation. It's simple trigonometry, nothing. And in case you have not understood here what is happening, let's say you have a point somewhere here which has at a distance r, and let's say some theta angle. So what happens here? You can always have a rectangle here. Again, sorry, a triangle here, and you can see that the height of the triangle turns out to be some kind of r sine theta, and this base turns out to be some kind of an r cos theta. And honestly speaking, this is what my x is, and this is what my y is. So this point P turns out to be x comma y, where you can see x is actually nothing more but r cos theta, and y is basically my r sin theta. So this is how you can convert your r theta in the terms of xy. This is what the interconversion you can have between the coordinate systems. And the choice of the coordinate system actually depends on what kind of a problem we are dealing with. Let's say in my problem I have a symmetry in the distance. Let's say my problem is designed in such a way that its distance from the origin is fixed, does not change, only angle is changing. Then I would prefer to work in my coordinate system, polar coordinate system. Okay, and let's say if my motion, let's say if my problem is designed in such a way that it either moves in x-axis or y-axis, then it is good to use my Cartesian coordinate system. So depending on the problem, depending on the symmetry you have in the problem, you decide your coordinate system, and based on that you start doing your work. So basically my A part tells you that are these two coordinates are same. So turns out to be you cannot have r negative, right? So yeah, this is definitely false. You can see here you have r turns out to be negative. Okay, and also you can see the angles to which they are described is also a wrong answer. Angles are different because you can write down where 5 pi by 4 as some 5 plus 5 by 4, and definitely that's not equal to pi by 4. That's true, right? They are off by pi degrees, honestly speaking. So, and since they have given this example, I would like to illustrate that if these 2 points are given to me, 2 comma pi by 4, and 2 comma 5 pi by 4, you can see that one of the point is over here, symmetrically placed at a distance 2, which makes an angle pi by 4, which is nothing but 45 degrees. So my second point, which is 5 pi by 4, turns out to be over here at a distance 2, where you can see that this is pi and this is my pi by 4. So basically these 2 points are antipodal points. You can say, diametrically opposite, you can say, for example. So yeah, you can have that kind of picture in your mind. So these 2 points are basically reflection symmetry with respect to the origin, you can say. So that's the idea here. I hope this teaches you this coordinate system. Probably might be useful in your questions. Let's say you might have a problem in terms of r theta. Probably, I don't know. Just in case. Here's the limit. This limit does not exist. Okay, that's a red flag itself. So what can you comment about this limit? Whether this limit exists or not. So the idea is that first we need to understand how f of x and g of x gonna behave, and if f of x, let me write down here. So the question they have asked me is for this: if this particular limit was in the form of 0 by 0, infinity by infinity, were some form, and we know that other forms can be converted into these forms. So if this was an indeterminate form, and we know what to do in this case, we do this L'Hopital rule, sorry, which basically tells me that this limit is nothing but is also equal to this, and the part of the question tells me that does not exist. So what you can comment about this? Is this possible? Do we have an example for this? That's an interesting question. Let's see an example. Let's see, for example, like x times of sine over 1 over x, where you have x tends to infinity. Let's see, is this true? This is what we are trying to understand, and I know that this can be written down in this way, and if I just do a change of coordinate, like instead of x I just take some 1 over h, I know this whole limit will just become, because if you do this change of coordinate, let's say 1 over h, let me use another variable t, for example. So if x tends to infinity, my t will tends to 0, right? That's what I did, a change of coordinates here, and wherever I see x, I will put it as 1 over t. So this whole limit business will just become this, and which we know it's 1. So for sure this has a limit. Limit exists. But what if I write this in this manner? I mean this exact same way. Which was earlier, but now take a derivative, because this sounds to me like some 0 by 0 form, right? So yeah, and this suggests me to take a L'Hopital rule, and let's check whether this is true or not. And we know sine will become as a cos 1 over x, and we have to take a multiplication of 1 over x square. And in the denominator also we have something called as 1 over x square. If we take, we can always cancel, right, because they are 0. They are very close to 0, but they are not exactly 0. So that's the main point. And the moment we take this turns out to be some 0, cos 0, and we know cos 0 is 1. So we see that in this case also the L'Hopital rule works. And L'Hopital rule should work because in the proof of the L'Hopital rule, we assume that this exists. We assume in the proof of the L'Hopital rule, which here I am trying to basically use. So I just showed you a counter example, right, where I just showed that this whole particular thing over here was nothing but this, right? And in case you're wondering, like this is my f of x and this is my g of x, I just showed that this derivative thing exists, which was 1. And so too as my original thing, which was this, also had this limit value, right, 1. So they were consistent. As the proof of the L'Hopital rule, we assume the ratios of the derivative limit also exist. So yeah, the statement is, in this case it is true because it is consistent what we had just discussed. So yeah, this is true because here it is very important. Does not exist together. They go together. If this exists, then definitely the other statement will also exist. Now let's go to the C part. Then we have this function f(x) for which the double derivative is 0. Then f has an inflation at x equal to c. Which is again repeat question, which we have just discussed earlier as well. You can see from T part over here. Like over here you can see this. Exact same question. Again, that's a repetitive. Next, let's go to the next part. We have also discussed this. This question is again same, but this C part is again same as what we have discussed here. Yeah, you can see this is a linear approximation because you can see this is a linear approximation of function. That's the right answer. And in case you didn't understand this, ask me, I'll create this again. Linear In case you didn't understand why this linear approximation of function, let me make a small note on it. Since we know that there is a function f of x, and we can always write down this function in this way as an infinite series, which is known as Maclaurin series. I can say special case of Taylor series. Which turns out to be f nth derivative. This means taking an nth derivative, substituting 0 in that, take an n factorial, and this is in general true. In general true, this can also be seen as Taylor series at x equal to 0. So we are basically writing down the series with respect to some reference point, and that reference point is actually x equal to 0. So whenever we take that x equal to 0 as a reference point in a Taylor series, we call that series as a Maclaurin series, which has a name like that. And the important idea is that if you see very carefully this series, this is nothing but just this, right? Double derivative Okay, so that goes, that's infinite terms. Okay, see. Okay, but the idea is that in the question they have asked me to calculate the linear approximation. In the question they have asked me to calculate what the linear approximation of f. So what does it mean by linear approximation? So linear approximation is that you will restrict your x very close to 0. You will just consider the neighborhood of the 0, because if you just consider neighborhood of the 0, that means all your higher order x square, x cube, x power 4 will be 0. You can just approximate them 0, right? You can just approximate them 0. So what happens basically in this linear approximation, all your higher order terms is 0. You just restrict yourself till here. That's what a linear approximation means. In order to do the linear approximation, you just need to know two things. You just need to know two things. So the first thing you should need to know is that value of function, value at x equal to 0. And second is derivative at x equal to 0. That's it. And you are done with your linear approximation. Right? So this is good, right? This is amazing. This is fantastic. Let's say you have a function like this, some random function, let's say, and let's say this was my x equal to 0. So you are just restricted. So you're restricting yourself just till here, only this much, very close to x equal to 0. So what I can do that in this small window, you can always approximate your any function as a linear approximation. And in order to know the linear approximation, basically this is enough. Basically you can always write down that f of x sum of 0 plus f dash 0 times x as a good approximation. Only in this video, in this window, the moment you went outside this window, this approximation will not hold good, right? Because you cannot just take x square, x cube and higher order powers to be 0, right? So that's the idea here. So just by knowing the value and the derivative, you can basically write down your neighborhood value. That's what it is done here, right? Because if I just show you this in another way, you will just get convinced yourself that we have already discussed this. I can write this as this, which is this, right? In case if you are not convinced yet, let me write down this way. This is again what the definition of limits we had. Exact same thing. So it's just a rewritten thing of the same good old thing. So this is what this statement and this question is trying to tell you, this E part. So I will suggest you to go through this, which is just basically the combination of this idea and this exact same idea what we have just discussed over here. There it is. Yeah, over here. So this is interesting. Now the f part basically asks you, like, every function is either an odd function or an even function. Is this true? Is this true? So first we need to understand what do you mean by even and odd function. So let me give you a clarification in case anyone of you have a doubt. Even function basically has this reflection symmetry. About y-axis. So this is some geometrical point of view. I mean to say, no, geometrically. But how do we see this algebraically? So what algebraically it means that if you, instead of x, you just substitute minus of x, and that is still equal to the positive counterpart, and they are equal. The negative is equal to the positive counterpart, and that's what we call as an even function. That's how even function is defined, and that's what algebraically it means, right? So this is what an even function. So now what about the odd function? What does it going to tell you? So I'll just make copy paste here. You have this important minus sign outside. So the negative counterpart is of opposite, equal and opposite to the positive counterpart. And let me show you, like, how can you see them. For example, this is your y-axis, right? This is your x-axis. You can see this is just nothing more but a reflection about the y-axis, right? And this is an anti-reflection about the z-axis, about the this is about the x-axis. I mean, not actually about the x-axis. I should say this is with respect to origin, about origin. So let's say you have something over here. You have done something. So you have just exact image on the other half, and that's the idea. So you see that, let's say you have a point here, just x comma f of x. So you have this minus x comma minus of, or you can see this is nothing but just f of x, this. But in the case of odd function, you will see this point to be over here, where it is minus x. Yeah, so you can say, these are the odd behavior, you can say. And over here you can see some kind of an even thing. So if you just look for the symmetry, if symmetry is with respect to the y-x, then it's an even function. Symmetry is about the origin, then you can say it's an odd function. And for the example of the even function, I would suggest is the cos x function, and for the odd function, I would suggest as an example as sine function. And the claim that now the claim I'm going to tell you that is very important claim. You should never forget this claim. And the claim is very simple, that any function can be written as sum of even function and odd function, always. How can we do that? Because I can always do this half times, we'll do this multiplication and division of 2, okay, and what we'll do again, we will add and subtract f of minus x, and what happens next, we have this f of x plus f of minus x, as this is a counterpart, and this. So over here you have this as an odd function, right? And this as your even function. This is your arbitrary function. So that's important. I hope you keep this in your mind. Okay. So every function can be written as sum of odd and even function. Similarly, the exact same thing also holds for the matrices as well. Let's say you have this matrix. Let's say you have a matrix, any general matrix. This matrix can be written as always sum of symmetric and anti-symmetric. In case those who know the matrix thing, they can just relate this out. You can just see it. They just cancel out. Okay. So this truth is also for the matrix as well. In the case of matrix, we don't have something called as even odd idea, but in the case of matrix, we have something called as symmetric and anti-symmetric idea. So the same thing also prevails in the case of matrices. So the next part, so what we see here, that's true. The statement is true. I hope this teaches you an interesting concept, an important concept. Now let's go back to the question and see the G part. A function that is continuous on a closed interval attains an absolute maximum value and an absolute minimum value at numbers in the interval. So the important term they have used, that the first important term is continuous on the closed interval. That's important. And inside that closed interval, it attains a maximum value and absolute minimum value in that interval. So the idea is this state can be false, and the reason I'm saying you that this can be false, you might have absolute maximum and absolute minimum at the boundary point, right? At the boundary point as well. This might not necessarily be equal to have this absolute maximum and minima inside the interval. You can still have at the boundary points, which are not the maxima. Again, let me show the diagram. That makes sense. Let's say you have this idea. Yeah, for example, this is x equal to a, and this is x equal to b. This is an enclosed interval, and you can see the absolute minimum is here and absolute maximum is here. So you can have maximum value and minimum values, absolute minimum, maximum at boundary points. But the local maximum and local minimum will be inside the boundary points. Talking about the local. Okay, so this is your local thing. Honest speaking, even this is also a local, but we don't consider them to be local. But might be. So that's wrong, because you can have the absolute maximum and minimum at the boundary, not just inside the interval. You might have to be very again cautious. And let's discuss the H part. So an ellipse is a set of all points in the plane, the sum of whose distances from two fixed points is a constant. So I guess we can skip this because this is related to the conic section, and I don't want to go inside that. We can just skip it. It's not a part of our syllabus. Let's go to the another point. This is an interesting question. Whether we have, suppose this is given to me, the summation of double derivative and the value of the function is 0, right? So this actually turns out to be the solution. So this is my actually a differential equation. So those who know what is differential equation, they can relate what I am trying to say. And if you solve this differential equation, you will find this solution. Okay, and it's claiming that the possible solutions will be either tan x sin x, sec x, or 1 over x. So what is the possible answer? Basically, you have to circle the correct one. B, the answer is B, because this is the one which solves the problem. To me, the answer is B, because if you take a double derivative of sin x, it will again give you sin x, but with a negative sign, right? And if you just substitute this, if you want to check this, you just substitute. You will see that double derivative of sin x plus sin x would be 0. So I'm just highlighting the answer here. So I would just suggest you to go and check this. This is your answer. And the next part they have asked me, we can skip this part because this has to do with inverse trigonometric function. So we will skip this. So skip. Okay. We will not solve this problem. It's not part of our course. Now we'll go to the next question, where we have a function fx that is told me to be a continuous function in the given interval a to b, and that's a differentiable in the open interval. That's important that the function is differentiable in the open interval, because we don't have definition at the boundary point. I mean, differentiability definition is not true at the boundary point. So that's why I have this open interval. So you have to make sure whether you understand this particular statement, because the difference of them can be a leading cause of the wrong answer. So, yeah. And such that the value of the function at a and b is given to me. So the question they have asked me, using the mean value theorem, we guarantee that there exists a point between a and b such that the instantaneous derivative at that point is equal to 4. And then we can check this. If we apply this mean value theorem, that has to be 10 minus 2 divided by p minus 7, and okay, on which interval? Okay, we have to select p and a such that this whole ratio turns out to be 4, right? Because the mean value theorem there exists, because that's a statement of the mean value theorem which we have discussed earlier. So you have to select a and b such that this whole calculation turns out to be true. And we can check from here that the p minus a turns out to be 4 divided by 8, which is half. That is true. Have I did a mistake here? Okay, sorry, I have made a mistake here. Okay, that is equal to 8 divided by 4, that is true. So the difference between a and b must be 2. So we'll check. So in the case, the A option, you can see the difference is not 2. In this case, the difference is not 2. Over here, I can see the difference of 2. I can see this is my answer. So this is how you solve the problem, and that's a very easy problem to solve. The idea is that a minus b has to be, b minus a has to be 2. In the t part, what we have is a p of t be a function which gives the population as a function of time. So assume that the p of t satisfies the natural growth equation, and at some point, okay, we will skip this. We'll skip this because this question demands you that you know what is the natural growth equation. So we'll skip this, not a part of syllabus. Anyway, this question is still doable because in case if you know, the growth equation is actually this minus some lambda of, well, this is growth constant, this is the growth constant. So yeah, everything is given to me. If you guys want to try this question, yeah, you can try, right? So that's the idea. You can do this problem. But maybe if you have this question in your exam, they would definitely give you this equation. Okay, so don't worry about it. So the next question is B. Suppose that function is continuous in A and B and differentiable on A and B. Okay, that's the same regular statement. And the new thing which you see here is that f of x is strictly increasing in the given interval. So what we can say that? So first of all, A option is wrong because A option tells you that function is decreasing. So definitely this is wrong. B option tells you that f has no local extremum. That's true. F has no local extremum. Because to have a local extremum, you need to have a solution, right? Because f of x is never equal to 0. Because extremum locations are basically at where the first derivative is 0. But you can see in the question they have not given to be 0. They are strictly positive. So definitely a function has no local extrema. So the C part is wrong because f is constant only when the first derivative is 0 throughout the whole interval. That's wrong. You can see it has a non-zero value. It's a positive thing. So that cannot be constant. The first thing which I said by looking into this f dash x greater than 0 to be as that's a strictly increasing function. And if you check the D part, where f is a concave up, is this a concave up? Yes, that's true. Concave up, that's true, right? Or is it false? So our answer is actually false. It can be both. F can be concave up, can be concave down. How can we know which is concave up and which is concave down? And the way you can know that which one is concave up, which one is concave up, down, when the second derivative is 0, greater than 0, and for the concave down, when the second derivative turns out to be negative. Right? In case if you are wondering how is this true, let's say we have this particular plot. You can see this is strictly increasing, right? You can have another plot which is this. This is also strictly increasing, but you can see one of the curve has concave up, another curve has concave down. Right? And if you see very carefully over here, f dash x greater than 0 is true for both. But over here, my double derivative is positive, but over here my double derivative is negative. And reason you can see how is it true? Because in the case of red line, I can see even the slopes are also increasing. Even the rate of change of slope is positive. But in the case of concave down, you can see from here that the slope is decreasing. I mean, first it had a very high slope and it has a very less slope. The value of slope is decreasing, even though the value of slope is positive. But the change of the slope is decreasing manner. So that's the idea. So that's why it's false. And if you see the E part, f has no zero. No zero in the sense mean to say no roots. So they are basically the same thing. When we see that this is true, might not be. For example, I can give you one example. For example, this f of x equal to e to the power x, and let's say this is defined from, for all x 0 to 1, for example. So what kind of a graph are you going to have? So you have something called as this. So you have 0 comma 1, and over here we have this 1 comma e, and you can see there is no root. So again you can see this is false. And the moment you got the right answer, then definitely all other options will be wrong, because the questions are designed in such a way that there is only one correct answer. So you must be confident in your answer with answer. Okay, and Okay, so the 13th question basically, again, it's a, you have to select the correct answer for this. Okay, so this is the complete question. So this 13th question basically, we have this equation, and the first part they ask, it has no real roots, exactly one real root, exactly two real roots. Then you have last option is exactly three real roots. Sorry, second last, then last is exactly five real roots. So first of all, I need to make clear that the number of roots is equal to the degree of equation. But you might have some roots which are real, some as complex. I would not use the word imaginary, I would say complex. You might have some of the roots to be real, some might to be complex, but if you sum all of them, that will be equal to the number of total roots, and that total roots is equal to the degree of equation. And in this question, you can see the degree is 5. It's the fifth degree equation. So definitely it has 5 5 roots. But the catch is complex roots comes in pair. Complex roots comes in pair, and you can further divide your real to be two parts. First is rational and irrational. Okay, so irrational also comes in pair. Okay, so in case if you are not clear with the idea which I have just showed you, let's say alpha is a complex number and that is root, then your the companion root, because complex root comes in a pair, so the companion root of the alpha would be just alpha star, which is the complex conjugate. So if you don't know this, I would add this complex conjugate. Similarly, if you have a irrational root, for example, some 2 plus root 3, so the companion root would be definitely conjugate root, like conjugate of the irrational, you can say. So this is an example, I would say. This is an example, and let me properly write this example as well in case you are getting confused. So let's say this is the companion root, I would say, where alpha beta belong to real, some real number. But the idea is, if this is z, some complex number, then this is z star, okay. And if this is q, then I would say this is q star. Star in the sense it's a complex of this, conjugate, I would say conjugate irrational root number, conjugate irrational. So let me write down this to be as conjugate irrational. So irrational comes in a pair. So complex number comes in a pair, and the idea of the pairs is in the means of conjugate. Okay, so we can say this to be as conjugate pair. You can say, but you can see irrational comes distinct. I mean, because in the case of rational, you don't have this under root thing. I mean, you have always a perfect thing, right? So you don't have the thirds involved in that. That's why the conjugate. So basically, that's self conjugate. Let me clear it. They're self conjugate. So yeah, that's self conjugate. That's the idea. I hope this tree will help you to solve many of the questions. And let's get back to the question. And the question tells you that this equation which has a degree 5, so definitely you have one real root, because you might have possibility, at least one real root. At least you might have 5 real root at max. Let me write it at most. At max is the wrong word. The word is at most, right? And what are the other possibility in between? Other possibility in between, you might have 3 real roots, maybe, right? 3 real roots, but you cannot have 2 real roots. You cannot have 4 real roots. Otherwise, you won't be able to justify the complex roots, right? Because your roots are either real or complex, and the idea is that the complex root comes in a pair, right? So you can see from here that since you have only five roots, in total we have 5 roots, but the number of real roots are odd number here, because the complex roots comes in a pair. So the number of complex roots will be always real, always even. So the idea is number of complex roots even number, and the number of irrationals roots are always even. At least 2, right? At least 2. So if we have total number of roots equal to 5, so the possibility of number of complex roots we have is either 0 number of complex roots, or you might have 2 number of complex roots, maybe 4 number of complex roots. So you have only these 3 possibilities, only this 3. And over here, if I write down the possibilities for the real roots, you might have 5 real roots, you might have 3 real roots, or you might have 1 number of real roots. So that's the idea. But if you are further interested in being rational and irrational, so in the case of 1, this will be for sure rational, because there is no way you can have a pair of irrationals inside. And in this case, you have 3 number of rational roots, or you can have 2 number of irrational roots plus 1 number of rational. At least you will be having at least 1 rational in this case, 1 rational root, right? And in the case of 5, you have possibilities of 5 number of rational roots. And what are the possibilities you can see here is 3 number of rational roots plus 2 number of irrational roots, right? And the next possibility you can see here is 1 number of rational root plus 4 number of irrational roots. So this is the tree of possibilities which I have shown you here. You can see the tree of possibility. Now you can see at max what we can have, at what minimum we can have. And let's see what is in the question itself. The question, so here you can see that no real roots. So that's definitely wrong. We have at least one real root. Then the B part basically tells you that exactly one real root. That's wrong. We can have all 5 of the roots to be real. Then C part tells you that exactly 2 real roots. Definitely wrong. Exactly 3 real roots. And E question tells you that exactly 5 real roots. So the way we can check. So what are possibilities we have? A possibility is definitely wrong. Exactly one real root could be. So we have to solve this. So the most probable option which we can see that, let me circle this. This could be one possibility, right? Exactly 2 real roots. This is definitely wrong. We saw that number of real roots has to be odd because complex roots comes in pair. Right? This could be possibility B, and this could also be possibility. So we have to solve this equation and check. So that's the only way we can further select down what is the answer and all. And one more important thing we can see here, the sum of all roots is 0. Okay, because sum of all roots would be, in this case, sum of all roots is actually has to do with, b a to the power n minus 1 upon a to the power n. So what is this? This is not power, this is notation. The notation is that, let's say you have an in general equation with, let me write down this to avoid confusion, because I don't want you guys to see this as a power. They are not power, because we can always write the in general equation to be as this, right? Sum a1 x plus a0 0. So you can see from here. Now you can see in the question, the a sub n minus 1 is 0, right? And in the coefficient of x to the power 4 is 0. So what you see here, the sum of all roots is 0. Maybe you can use this as an idea to further, to figure out. So, and you can also see that sum of pairs of group, let's say this is another pair and this is another pair. This is also 0, because this actually turns out to be this. It is also 0 in this case. So I will further discuss this. If you have a guys problem in question, we can further discuss this. For now, we are done with our session. But you can check them. You can check this. This is known as theory of equation. You can find all these things, something called as under the hood of theory of equations. In case if you are interested to take a look, a detailed look, you can find that. We have some relation between our coefficient of equation with the properties followed by the roots. So this is basically sum in pairs, sum of pairs, product pairs. I mean, write down properly. Sum of product of pairs, that turns out to be this kind of a coefficient, and the problem we can see that's turned out to be 0. So maybe we can use this silly tricks further, without solving the problem, we can further short down what is the answer. So Okay, so you guys can try the other questions. Other questions are just repetitive what we have did earlier. So if you get stuck somewhere, just email me. I will send you the solution. Maybe we can discuss one of those questions in our next session. Okay. Actually, I'm lacking a behind. I'm lacking a bit because I must should have covered optimization and other numerical methods because we haven't discussed them yet. So from the next session, I'll talk more on optimization and numerical methods. Does anyone have questions so far? Any question? Any suggestion? If not, then we can close the session. Hope you guys are doing well. Uh, from the next section, I will take the questions from the previous year and previous year's assignment, and I'll solve them. And let's see like how you guys perform well. And hopefully, questions are useful that what so far I've discussed. So see you guys on the next session. Okay. Bye.